The cosmos is a story written across an infinite canvas, and you are about to read every page. This is the ultimate guide to absolutely everything in the universe, a single epic journey from the first spark of reality to its final whispered end. By the time we finish, you will hold a complete mental map of existence, from the tiniest quantum flutter to the grand sweep of galactic superclusters. We will start at the explosive birth of space and time itself, where all the rules were written in a fire far hotter than any star. We will chase light into the hearts of black holes, where gravity bends the universe into knots, and confront the ghostly twins of dark matter and dark energy that command our fate. We will ask if we are alone on this pale blue dot, and wonder if our universe is just one page in an endless library of realities. How does it feel to finally see the whole picture? Our story begins not with a bang, but with a silence so profound it defies description. There was no before, no place for it to happen, no outside to watch. There was only a single, unimaginable point containing all the energy, all the potential for every galaxy, star, and atom that would ever exist. We call this the Big Bang, but that name is a cosmic misdirection. This was not an explosion into space. It was the explosive birth of space and time themselves, an event where the very fabric of reality began to stretch and swell from that initial singularity. Think of the universe not as a fireball in an empty room, but as the room itself being built at a staggering speed. Every point of space began rushing away from every other point. A useful, if imperfect, analogy is a loaf of raisin bread dough in an oven. As the dough bakes and expands, every raisin moves away from every other raisin. From the perspective of any single raisin, all the others are receding. No raisin is at the center of the expansion. The center is in the dough itself. That is our universe. We are not flying away from a central point. We are embedded within the stretching canvas of space-time. The evidence for this incredible origin is etched across the sky. The first and most profound clue is the cosmic microwave background radiation. About 380,000 years after the Big Bang, the universe had expanded and cooled enough for atoms to form, allowing light to travel freely for the first time. That primordial light, released in a brilliant flash, has been stretching and cooling with the expanding universe for over 13 billion years. Today, it reaches us not as visible light, but as a faint, cold microwave static that fills every direction of space. This is the universe's baby picture, a snapshot of its infancy, and its uniform glow is the afterglow of creation itself. The second major piece of evidence is the redshift of distant galaxies. When astronomers look at the light from galaxies beyond our own, they find its color shifted toward the red end of the spectrum. This is because the space between us and that galaxy is expanding, stretching the wavelength of the light as it travels, much like the sound of a receding siren drops in pitch. The farther away a galaxy is, the faster it appears to be receding, and the more its light is redshifted. This observation tells us the universe is not static. It is actively growing, carrying galaxies along for the ride on the river of expanding space. So we begin with a singularity, a point of infinite density where our known laws of physics simply break down. From that state, space unfurled, time began its forward march, and the entire cosmic story was set into motion. But this raises an even more perplexing question. If everything started from a single, unimaginably hot point, how did it become so smooth and uniform? How did the seeds for galaxies get planted in that first fiery moment? The answer lies in a concept even more dramatic than the Big Bang itself, a fleeting instant of hyperinflation that set the stage for everything to come. To understand the universe's grand architecture, we must start with its smallest, most stubbornly fundamental pieces. Beneath every atom, beneath every whisper of energy, lie the true building blocks of reality, particles so small they have no internal structure at all. These are the quarks and the leptons. Think of them as the universe's ultimate, indivisible Lego bricks. Quarks are the social ones, always found in groups, bound together by the strong nuclear force to form protons and neutrons. Leptons are the loners, with the most famous being the electron, the negatively charged particle that whizzes around an atom's nucleus. But these particles do not simply exist in silence. They are in a constant, frenetic conversation governed by four fundamental forces. The strong force glues atomic nuclei together. The electromagnetic force dictates how light travels and how atoms bond. The weak force drives radioactive decay, and gravity, the most familiar yet in many ways the most mysterious, sculpts the large-scale structure of everything we see. This is the foundation, a handful of particle types and a quartet of forces written into the laws of reality during those first moments after the Big Bang. From this subatomic chaos, structure begins to emerge. When quarks combine into protons and neutrons, and a cloud of electrons is held in orbit by the electromagnetic force, you get an atom. Hydrogen, the simplest atom with just one proton and one electron, was the first and remains the most abundant element in the cosmos. Under the crushing pressure and immense heat inside the first stars, these hydrogen atoms fused together, a process called nuclear fusion. This stellar alchemy forged heavier elements like helium, carbon, oxygen, and all the way up to iron. When those early stars died in spectacular supernova explosions, they scattered these newly forged elements across space like cosmic seeds. These elements could then cool, clump together, and form molecules, the next step in complexity. Simple molecules like water or carbon dioxide are the precursors to everything more complex, from the dust grains in a nebula to the chemistry of life itself. Now scale the view up dramatically. Vast clouds of this gas and dust, enriched with heavy elements, begin to collapse under their own gravity. As a cloud contracts, it spins faster and flattens into a disk. At the furious, dense center, pressure and temperature soar until nuclear fusion ignites and a star is born. The leftover material in the disk coalesces into planets, asteroids, and comets. This is how our solar system formed around the Sun 4.6 billion years ago, a single story repeated trillions of times across the galaxy. Stars are not scattered randomly. They are often born in giant clusters from the same stellar nursery, and they live out their lives orbiting the center of a galaxy, a colossal island of hundreds of billions of stars, all bound together by gravity. Our home is the Milky Way, a majestic spiral galaxy with arms of stars, gas, and dust spinning around a supermassive black hole at its heart. But the scaling does not stop at galaxies. Look out into the deepest reaches of space, and you see that galaxies themselves are not scattered like lonely islands in an empty sea. They gather into groups and clusters, which in turn form the largest structures in the known universe, vast filaments and sheets of galaxies that stretch for hundreds of millions of light years. These filaments intersect like the strands of a cosmic spiderweb, surrounding immense, nearly empty regions called voids. This is the cosmic web, the large-scale structure of the universe, a frothy, bubble-like architecture traced out by the glow of 100 billion galaxies. It is a breathtaking hierarchy, a Russian nesting doll of reality. From the frantic dance of quarks to the silent, slow-motion waltz of galaxy superclusters, it is all connected by the same simple rules written at the dawn of time. Yet for all this majestic structure, most of the universe is made of stuff we cannot see. The gravity that holds fast spinning galaxies together and weaves the cosmic web is far stronger than the pull of all the visible stars and gas. Something invisible is doing the heavy lifting, a ghost in the cosmic machinery we call dark matter. But this grand cosmic web, these islands of light, all trace their lineage back to a single, ordinary star in a quiet spiral arm. Our cosmic address is a modest one, a pale blue dot orbiting a yellow dwarf star we call the Sun. our solar system is not just a collection of planets, it is a forensic record of its own violent and beautiful birth. It all began 4.6 billion years ago within a giant, spinning cloud of gas and dust known as the solar nebula, a fragment of a much larger molecular cloud seeded with the heavy elements from long-dead stars. As this cloud collapsed under its own gravity, it spun faster and flattened into a vast, hot disk. In the searing center, hydrogen atoms were squeezed together with such force that nuclear fusion ignited and our sun was born. The leftover material in the disk, now a chaotic whirlwind of rock, metal, and ice, began to clump together through countless collisions, forming planetesimals, the building blocks of planets. A critical line, known as the frost line, existed in this young disk. Inside this line, close to the sun's heat, only metals and rocky minerals could remain solid. Beyond it, volatile compounds like water, methane, and ammonia could freeze into solid ice. This simple thermal divide created the two families of planets we see today. The inner solar system gave us the terrestrial or rocky planets Mercury, Venus, Earth, and Mars. These are dense worlds of iron and silicate rock forged in the furnace close to the sun. The outer solar system, beyond the frost line, became the realm of the gas giants Jupiter and Saturn, and the ice giants Uranus and Neptune. Here, cores of rock and ice grew massive enough to capture the vast primordial envelopes of hydrogen and helium gas that still swirl around them today. But each world is a unique chapter in this story, holding profound mysteries. Venus, often called Earth's twin in size, is a terrifying lesson in a runaway greenhouse effect. Its thick carbon dioxide atmosphere traps solar heat so efficiently that surface temperatures soar to nearly 900 degrees Fahrenheit, hot enough to melt lead under crushing pressures and acid clouds. It is a vision of a climate catastrophe taken to its ultimate extreme. Jupiter, the solar system's titan, is a stormy, swirling world of banded clouds. Its most famous feature, the Great Red Spot, is a colossal anticyclone larger than Earth that has raged for at least 350 years, a perpetual hurricane in an alien sky. Perhaps the most tantalizing mysteries, however, lie not on the planets but in the shadows of the giants. Moons like Jupiter's Europa and Saturn's Enceladus are frozen worlds with solid ice crusts. But beneath that ice, gravitational flexing from their giant planets likely keeps vast global oceans of liquid water churning. At Enceladus, geysers of water vapor and ice crystals erupt from cracks near its south pole, spraying evidence of this hidden sea into space. These dark subsurface oceans, warmed not by sunlight but by tidal forces, are the most promising places in our solar system to look for life beyond Earth. And then there is our world, suspended in a delicate and precious balance. Earth orbits within the Sun's habitable zone, where temperatures allow liquid water to exist. Our planet retained a protective atmosphere and a magnetic field that deflects deadly solar radiation. A stabilizing moon moderates our axial tilt, preventing wild climate swings. Geological activity recycles carbon, regulating our temperature. This confluence of factors, this rare and fragile alignment, is what makes our pale blue dot an oasis of life in the silent cosmic desert. We are the product of a specific and violent history, living on a world that is the exception, not the rule. Yet for all the diversity of planets and moons, they are merely the silent spectators to the true drama of the cosmos. The real action, the engine that drives the entire story, is happening in the hearts of the stars themselves. Every star is a titanic furnace, a place of unimaginable pressure and heat where the very elements of life are forged. Their story begins with gravity. A vast cloud of gas, primarily hydrogen, begins to collapse under its own weight. As it shrinks, it heats up, just like the air in a bicycle pump gets warm when you compress it. At the core of this collapsing cloud, temperatures reach millions of degrees, and pressures become so intense that something miraculous happens. Hydrogen atoms, which normally repel each other, are slammed together with such force that they fuse, creating a new, heavier element, helium. This process is nuclear fusion, and it releases a staggering amount of energy in the form of light and heat. That energy, radiating outward, pushes against the crushing force of gravity, and a perfect, stable balance is struck. A star is born, and it enters the longest, most stable phase of its life, what astronomers call the main sequence. Our Sun has been in this phase for about 4.6 billion years, and it has roughly 5 billion more to go. It is a cosmic equilibrium, a sustained explosion held in check by its own gravity. But a star's fate is written in its birth weight. How it lives and how it dies depends entirely on how much fuel, how much hydrogen it started with. The smallest stars, the red dwarfs, are frugal with their fuel. They burn slowly and dimly, and their gravitational grip is so gentle that they can fuse nearly all their hydrogen over trillions of years. These stars will fade peacefully, eventually cooling into dark, cold cinders known as black dwarfs, a fate so distant that the universe is not yet old enough for any to exist. A star like our Sun, however, faces a more dramatic end. After billions of years on the main sequence, it will finally exhaust the hydrogen in its core. With no fusion energy to push back, gravity wins for a moment, causing the core to contract and heat up even further. This new heat ignites the shell of hydrogen around the core, causing the outer layers of the star to swell dramatically. The Sun will become a red giant, its outer atmosphere expanding to engulf the orbits of Mercury and Venus, and likely rendering Earth uninhabitable. But within this swollen, cooling exterior, the core continues its desperate fusion, now creating carbon and oxygen. Eventually, these outer layers are gently blown away into space, forming a beautiful, glowing shell of gas called a planetary nebula. At the center, the hot, dense core of carbon and oxygen is left behind exposed. This is a white dwarf, an Earth-sized remnant with the mass of a star, shining only with leftover heat. It will take hundreds of billions of years to cool completely, a dying ember in the cosmic dark. For the most massive stars, the story ends not with a whisper but with a scream. These titans burn through their hydrogen fuel in just millions of years, not billions. When their core runs out of fuel, the collapse is catastrophic. The temperatures and pressures become so extreme that fusion races ahead, creating heavier and heavier elements in layers like an onion all the way up to iron. But iron is fusion's dead end. Fusing iron does not release energy, it consumes it. In an instant, the star's support vanishes. The core collapses at nearly a quarter the speed of light, and then rebounds in a shockwave of unimaginable violence. The star explodes as a supernova, outshining its entire galaxy for a few glorious weeks. In that apocalyptic inferno, temperatures soar so high that elements heavier than iron are forged: gold, silver, uranium, all the complex atoms that make up our world and our bodies. This stardust is then blasted across the galaxy, seeding future generations of stars and planets. What remains after the supernova is just as incredible. If the core is between about 1.4 and 3 times the mass of our Sun, it collapses into a neutron star. A single teaspoon of this material would weigh as much as a mountain, a sphere only the size of a city where matter is compressed into a sea of pure neutrons. Some neutron stars spin rapidly, beaming out pulses of radiation like cosmic lighthouses, which we detect as pulsars. And if the core is more than about 3 times the mass of the Sun, nothing in the universe can stop the collapse. It continues forever, crushing itself out of our visible reality and leaving behind only its gravity, a point of infinite density. A black hole is born. Every element in your body, except the primordial hydrogen, was cooked in the heart of a star or forged in the death throes of a supernova. We are literally made of star stuff, the ashes of cosmic giants that lived and died long before our Sun was even a dream in a cloud of gas. The most violent death of a star does not end with fading light, but with a final, permanent silence. That collapsing core, too massive to become a neutron star, continues its inward fall forever, crushing itself into a point of infinite density called a singularity. Around this point, gravity becomes so intense that not even light can escape. The boundary of no return is called the event horizon. It is not a physical surface, but a mathematical line in space, a one-way membrane. Cross it and you are cut off from the rest of the universe for all time. The physics here does not just bend the rules, it shatters them. Space and time swap roles. The direction toward the singularity is no longer a place you can move through, but a future moment you are inevitably pulled toward. For an object falling in, the effects are grotesquely poetic. The pull of gravity on your feet would be vastly stronger than on your head, stretching you into a long, thin strand of atoms in a process aptly named spaghettification. You would be torn apart by tides of gravity long before reaching the central singularity. Yet black holes are not cosmic vacuum cleaners, randomly sucking in everything around them. Their gravity works just like that of a star or a planet. If you replaced our sun with a black hole of the same mass, Earth would continue orbiting the dark point in space just as it does now, though we would, of course, freeze in the eternal night. The truly monstrous black holes lie not in the remnants of dead stars, but at the very hearts of galaxies. These are supermassive black holes with masses millions or even billions of times that of our sun. They are not the corpses of single stars, but ancient beasts that grew by feasting on gas, dust, and stars over cosmic time. Our own Milky Way orbits such a quiet giant named Sagittarius, a star. For decades, these objects were only inferred by the frantic orbits of stars around an invisible, massive anchor. Then, in 2019, humanity saw one for the first time. The Event Horizon Telescope Collaboration, a global network of observatories working as one planet-sized dish, unveiled an image of the supermassive black hole at the center of the galaxy M87. We did not see the black hole itself, but its shadow, a dark silhouette against the glowing, swirling disk of superheated gas being pulled toward the event horizon. It was a ring of fire around a hole in space-time, a direct glimpse of the universe's most extreme environment. Another window opened just a few years earlier with the detection of gravitational waves, ripples in the fabric of space-time itself. When two black holes spiral toward each other and finally merge, they shake the cosmos like a bell. In 2015, the LIGO Observatory felt that chime from a collision over 1 billion light-years away. It was the sound of two black holes, one about 36 times the mass of the Sun and the other 29, becoming one. Since then, we have heard dozens of these cosmic mergers, a new astronomy that listens to the universe rather than looking at it. But for all we have learned, black holes pose profound puzzles that challenge our understanding of reality itself. The information paradox asks what happens to all the information about the matter that falls in. Quantum physics says information cannot be destroyed, but general relativity says it is lost forever behind the event horizon. Stephen Hawking proposed a startling solution that black holes are not perfectly black. Due to weird quantum effects at the very edge of the event horizon, they should slowly leak particles, a faint glow we call Hawking radiation. Over trillions upon trillions of years, this process would cause a black hole to evaporate completely. But what happens to the information it swallowed? The debate continues, a frontier where our two great theories of reality, quantum mechanics and general relativity, meet and fiercely disagree. Black holes are not just monsters, they are the universe's ultimate laboratories, testing the laws of physics to their breaking point. These stellar engines are not scattered randomly across the void. They gather into immense gravitationally bound cities, the galaxies. Each galaxy is an island universe containing hundreds of billions of stars, vast clouds of gas and dust, and an even vaster, invisible halo of dark matter that holds the entire structure together. They come in several majestic forms, each telling a different story of cosmic evolution. The most iconic is the spiral galaxy, like our own Milky Way. Picture a colossal pinwheel spinning in the darkness. At its heart lies a bright, spherical bulge of older, redder stars. Extending from this bulge are sweeping, graceful arms that spiral outward, tracing paths through a thin, rotating disk. These spiral arms are not solid structures, but density waves like cosmic traffic jams, where gas and dust are compressed, triggering the birth of brilliant new stars and glowing nebulae. Our solar system resides in one of these spiral arms, about halfway out from the galactic center. Surrounding the entire luminous disk is a vast, diffuse spherical halo of ancient star clusters, and we believe the dominant presence of dark matter. And at the very center of most spirals, including our own, lurks a supermassive black hole, a quiet gravitational anchor. Then there are the elliptical galaxies. These are the cosmic elders, appearing as smooth, featureless footballs or spheres of light. They contain mostly older, red stars and very little of the gas and dust needed to form new ones. They are like stellar retirement communities, the result of a quieter life or, more often, of violent mergers that used up all their star-forming fuel in one colossal burst. Their sizes range from dwarf ellipticals, barely larger than a star cluster, to colossal giants, the largest galaxies in the universe, which can dominate the centers of galaxy clusters. Finally, we have the irregular galaxies. These are the cosmic misfits, lacking any defined spiral or elliptical shape. They are often chaotic, ragged, and rich in gas and dust, leading to vigorous star formation. Many irregulars are the result of gravitational interactions or collisions with other galaxies, their neat structures torn apart by cosmic violence. The shapes we see are not permanent. Galaxies are dynamic, living systems that evolve over billions of years, and their primary driver of change is collision. Because space is so vast, stars within galaxies almost never hit each other during a merger. Instead, the galaxies pass through one another, their gravitational fields tangling in a slow, billion-year dance. This process violently stirs the gas clouds, triggering ferocious waves of new star formation, and can ultimately strip away the gas needed to make more. The delicate spiral arms are shredded, and the galaxies eventually merge into a single, new entity, often an elliptical galaxy. Our own Milky Way is on a collision course with its largest neighbor, the Andromeda Galaxy. Right now, Andromeda is a faint smudge of light in our night sky, but it is hurtling toward us at about 250,000 miles per hour. In roughly 4 billion years, the two great spirals will begin their first close pass, stretching and distorting each other with tidal forces. Over the next several billion years, they will swing around and merge, their stars mixing into a new, likely elliptical galaxy that astronomers have nicknamed Milkomda. The view from Earth, should any life remain here, would be spectacular, with the night sky filled with a dazzling chaos of new stars and glowing gas. The true beauty and diversity of these island universes has been unveiled by our greatest eyes on the cosmos. The Hubble Space Telescope, peering from Earth orbit, delivered iconic images of swirling spirals, dramatic collisions like the antennae galaxies, and the deep field views that showed thousands of galaxies in a patch of sky the size of a grain of sand held at arm's length. Now the James Webb Space Telescope, seeing in infrared light, pierces through cosmic dust to show us the newborn galaxies of the early universe, their structures being built in the chaotic dawn of time. These images are not just pretty pictures, they are chapters in the story of cosmic structure, showing us how these islands of stars are born, live, and transformed through epic encounters. Yet for all their splendor, the visible stars in a galaxy are merely the decoration on a far larger, invisible framework. The true architect of the cosmic web, the hidden hand that sculpts these islands and binds them together, is something we cannot see at all. The glittering cities of stars we call galaxies are built upon a ghostly foundation. For decades, astronomers have known something was deeply wrong with the cosmic ledger. When they measured how fast stars orbit the center of a spiral galaxy, they expected the outer stars to move slower, just as Pluto orbits our Sun more sluggishly than Earth. The gravity from all the visible mass at the galaxy's bright center should dictate this slowdown, but the observations revealed something astonishing. Stars far out in the galactic suburbs were whipping around just as fast as those near downtown. The only explanation is that there is far more mass in the galaxy than we can see, mass that is not concentrated in the center but spread throughout a vast, invisible halo. This mass, this missing gravity, is dark matter. It does not emit, absorb, or reflect light, making it completely transparent. We only know it's there because of its gravitational pull on the things we can see. Another profound piece of evidence comes from gravitational lensing, a dramatic effect predicted by Einstein. Massive objects warp the fabric of space-time, bending the path of light that passes near them. When astronomers look at massive galaxy clusters, they often see distorted, stretched, and magnified images of galaxies far behind them. The amount of bending is far greater than the visible mass of the cluster can account for. An immense, unseen mass must be present, acting as a cosmic lens. This invisible scaffold is not just holding galaxies together, it shaped the entire universe. The patterns in the cosmic microwave background, that baby picture of the universe, show tiny temperature variations that are the seeds of future galaxies. The size and distribution of those seeds tell us precisely how much matter was in the early cosmos, and the answer is about 5 times more than all the atoms we can tally. Dark matter provided the gravitational wells for normal matter to fall into, allowing stars and galaxies to form. Yet for all its dominance, we still do not know what it is. It is not made of atoms. It does not interact with the electromagnetic force, so it passes through normal matter like a ghost through a wall. Leading candidates are hypothetical particles like WIMP, weakly interacting massive particles that could be streaming through your body by the billions every second without a trace. While dark matter pulls the universe together with its gravity, an even more mysterious force is tearing it apart. In the late 1990s, 2 teams of astronomers made a discovery that shook cosmology to its core. By observing distant supernova, the explosive deaths of white dwarf stars, they could measure how fast the universe was expanding in the past. They expected to find that the expansion was slowing down over time, as the collective gravity of all the matter in the cosmos pulled back on it. Instead, they found the expansion is speeding up. Something is pushing galaxies apart with ever-increasing force. We call this something dark energy. It is not matter at all, but a property of space itself. Empty space, according to our best theories, is not nothing. It has a baseline energy, and this energy exerts a negative pressure that causes space-time to stretch. Think of the universe as a loaf of that raisin bread dough again, but now the oven itself is causing the dough to rise faster and faster. The most unsettling part is the cosmic budget. When we add up everything we understand, the ordinary atoms that make up stars, planets, and us, they constitute a mere 5% of the total content of the universe. Dark matter, the invisible glue, makes up about 27%. The remaining 68%, the overwhelming majority of everything, is dark energy, the force of cosmic repulsion. We live in a universe dominated by entities we cannot see, governed by forces we do not fully understand. The story of the cosmos is written in a language we are only beginning to decipher, a tale where the actors are, for now, only shadows on the cave wall. If dark matter and dark energy are the unseen architects of the cosmos, then life is its most fragile and precious creation. The ultimate question hanging over our cosmic story is a simple, haunting one. Are we alone? The field of astrobiology seeks to answer it, merging astronomy, biology, and geology to understand the conditions for life anywhere. The most fundamental concept is the habitable zone, often called the Goldilocks zone. This is the region around a star where temperatures are just right, not too hot and not too cold for liquid water to exist on a planet's surface. Water is the universal solvent, essential for the chemistry of life as we know it. Our Earth orbits snugly within the Sun's habitable zone, a fortunate piece of cosmic real estate. But our own planet has taught us that life is stubborn, thriving in places we once thought utterly inhospitable. These organisms are called extremophiles. We find bacteria flourishing in the superheated water of deep-sea hydrothermal vents under immense pressure and in total darkness. We find microbes locked in Antarctic ice, surviving in the briny, sub-zero lakes beneath glaciers. There are even hardy creatures called tardigrades or water bears that can withstand the vacuum of space, extreme radiation, and years of complete dehydration. If life can exist in boiling acid, in crushing depths, and in frozen deserts on Earth, then the range of possible habitats on other worlds expands dramatically. The first step in the search is finding the worlds themselves. For centuries, planets outside our solar system, called exoplanets, were purely theoretical. Now we know of thousands thanks to ingenious detection methods. The transit method watches for a tiny, periodic dip in a star's brightness as a planet crosses in front of it. This tells us the planet's size and orbital period. The radial velocity method looks for a star's subtle wobble caused by the gravitational tug of an orbiting planet. This reveals the planet's mass. With these techniques, we have built a catalogue of alien solar systems, many utterly unlike our own, with hot Jupiters orbiting blisteringly close to their stars or planets circling binary star systems like Tatooine from Star Wars. Among the most tantalizing discoveries is the TRAPPIST-1 system, a compact family of 7 Earth-sized worlds orbiting a small, cool red dwarf star about 40 light-years away. Remarkably, 3 of these planets orbit within the star's habitable zone. They are likely tidally locked, with one side in permanent day and the other in eternal night, but the twilight band between could be temperate. While red dwarf stars are prone to violent flares, the possibility of multiple rocky worlds with the potential for liquid water in a single system is a profound hint that Earth-like worlds may be common. This explosion of discovery makes the silence even more puzzling. This is the Fermi paradox, named for physicist Enrico Fermi. The universe is ancient and unimaginably vast, with hundreds of billions of stars in our galaxy alone. If even a tiny fraction host intelligent civilizations, many should have arisen millions of years before us. Given enough time, a civilization could theoretically colonize the entire galaxy. So, where is everybody? Why do we see no signs, no signals, no artifacts? The proposed solutions range from sobering to strange. One chilling idea is the Great Filter. This suggests there is a step in the evolution from simple chemistry to a spacefaring civilization that is almost impossible to pass. It could lie in our past, meaning the origin of life itself is miraculously rare, and we have already beaten astronomical odds. Or more worryingly, it could lie in our future, a common catastrophe like self-destruction through technology or an unavoidable natural disaster that prevents any civilization from reaching the stars. Other solutions are less bleak but equally mind-bending. The zoo hypothesis suggests advanced civilizations are out there but have chosen to observe us from a distance, like we observe animals in a preserve, enforcing a galactic non-interference policy. Perhaps interstellar travel is simply too difficult or too costly, or maybe civilizations communicate in ways we cannot yet perceive, using neutrino signals or something beyond our physics. Or the darkest possibility, maybe intelligent life inevitably turns inward, creating immersive virtual realities so compelling that no one ever looks up at the stars again. Our search is just beginning. Rovers on Mars drill into ancient lake beds, sniffing for chemical fossils. Future missions will sail the hydrocarbon seas of Saturn's moon Titan or fly through the plumes of Enceladus, analyzing droplets from its hidden ocean. And giant telescopes, both on the ground and in space, will soon study the atmospheres of distant exoplanets, looking for the chemical fingerprints of life like oxygen or methane in unnatural combinations. Every new world we find is a new page in a story we are only starting to read. The answer to whether we are alone will redefine our place in the cosmos, transforming humanity from a solitary voice in the dark into either a lonely miracle or a member of a vast, silent community. The profound silence we perceive in the cosmos might be a consequence of physics itself, a universe operating under a set of rules far stranger than our everyday experience suggests. For centuries, Isaac Newton's clockwork universe, where time was absolute and space a fixed stage, seemed perfectly sufficient. Then came Albert Einstein. His theories of relativity did not just tweak the old rules, they rewrote the entire playbook for reality, revealing a cosmos where space and time are woven into a single, dynamic fabric called spacetime. Special Relativity, published in 1905, began with two simple but radical postulates. First, the laws of physics are the same for all observers moving at constant speed. Second, the speed of light in a vacuum is constant for everyone, no matter how fast you are moving toward or away from its source. This second idea is the true mind bender. If you are in a spaceship chasing a beam of light and you measure its speed, you will still get the same number as someone standing still. To make this constant speed work, something else has to give, and that something is time itself. Time is not universal. It flows at different rates depending on how fast you are moving. This is time dilation. Imagine a pair of identical twins. One stays on Earth while the other embarks on a journey to a distant star in a spacecraft traveling at a significant fraction of light speed. From Earth's perspective, time on the speeding ship appears to crawl. Clocks tick slower, heartbeats slow, all processes decelerate. When the traveling twin returns after what felt like a few years to them, they would find their Earth-bound sibling has aged decades. This is the famous twin paradox, and it is not science fiction. We have measured this effect with extraordinary precision using atomic clocks on fast-flying jets and satellites. GPS satellites orbiting Earth must have their clocks constantly corrected for this relativistic slowdown, or their navigation signals would be useless within minutes. But special relativity dealt with constant motion in straight lines. Einstein spent the next decade grappling with acceleration and gravity, culminating in his masterpiece, General Relativity, in 1915. Here, he made an even more profound leap. Gravity is not a mysterious force pulling objects together across empty space. Instead, mass and energy tell spacetime how to curve, and curved spacetime tells objects how to move. The classic analogy is a stretched rubber sheet. Place a heavy bowling ball in the center, and it creates a deep dimple. Now roll a marble across the sheet. It will not travel in a straight line. It will curve inward, orbiting the bowling ball as if pulled by a force. The marble is simply following the shortest path, called a geodesic, through the curved geometry of the sheet. Earth orbits the Sun not because it is being pulled by an invisible string, but because it is rolling along a groove in spacetime curved by the Sun's immense mass. This curvature explains everything from the fall of an apple to the bending of starlight around the Sun, an effect confirmed during a solar eclipse in 1919 that made Einstein a global celebrity. And just as speed affects time, so does gravity. The stronger the gravity, the more spacetime is curved and the slower time passes. At the surface of a neutron star, time would crawl to a near halt compared to a distant observer. Fall toward a black hole, and from the outside you would appear to freeze in time at the event horizon, your image redshifted into oblivion. These are not mathematical quirks, they are the operational system of our universe. Space and time are not a passive backdrop, they are active dynamic players, stretched and warped by every star, every planet, and every bit of matter. This means the universe we see is not a collection of objects in space, but a complex, evolving sculpture made of spacetime itself, and we are all just moving along its contours. Einstein's curved spacetime describes the cosmos on its grandest scales, but down in the basement of reality, a completely different set of rules takes over. The quantum realm is a place where logic seems to unravel, and the universe operates on pure probability. This is the domain of the impossibly small, where particles like electrons and photons behave in ways that defy every intuition built from our macroscopic world. The first and perhaps most baffling rule is superposition. In our everyday experience, an object is in one place at one time. A coin flipped is either heads or tails. But in the quantum world, a particle like an electron does not have to choose. Until it is observed or measured, it can exist in a blend of all its possible states at once. Think of it not as a coin that is heads or tails, but as a coin that is spinning so fast it is both heads and tails simultaneously. This is not just a theoretical idea. It is the fundamental principle behind technologies like quantum computers, which use quantum bits or qubits that can be a 1, a 0, or a probabilistic mix of both, allowing them to perform calculations impossible for classical machines. Then there is entanglement, a phenomenon Einstein famously dismissed as spooky action at a distance. Imagine creating two particles that are intimately linked like a pair of magical dice. You separate them by any distance, sending one to the other side of the galaxy. When you roll one die and it comes up 6, the other die instantly shows a 6 as well, no matter how far apart they are. This is not communication, it is a deeper connection. The particles do not have individual properties until measured, they share a single quantum state. Measuring one instantly determines the state of the other, a correlation that appears to happen faster than light. Experiments have repeatedly confirmed this weird linkage, proving that at a fundamental level, the universe is non-local, interconnected in ways that transcend space. Governing this probabilistic fog is Heisenberg's uncertainty principle. It states that you cannot know both the exact position and the exact momentum of a particle at the same time. The more precisely you pin down one, the more fuzzy the other becomes. It is not a limitation of our instruments, it is a built-in feature of reality. The universe at its core is not a clockwork mechanism but a game of chance, a cloud of probabilities. This quantum rulebook is what makes atoms stable, dictates how chemicals bond, and allows the nuclear fusion in stars to proceed. Without these strange laws, electrons would spiral into atomic nuclei, chemistry would not exist, and neither would we. Yet here lies the greatest unsolved puzzle in all of physics. The elegant, deterministic curvature of Einstein's general relativity, which explains gravity and the cosmos, is utterly incompatible with the fuzzy, probabilistic chaos of quantum mechanics, which explains atoms and forces. One theory rules the very large, the other the very small, and they refuse to speak the same language. This schism becomes catastrophic in places like the singularity inside a black hole or the first instant of the Big Bang, where enormous mass is compressed into a microscopic volume. Our two most successful theories of reality break down, screaming at each other in mathematical discord. The holy grail of modern physics is a theory of everything, a single framework that seamlessly unites quantum mechanics and general relativity. Candidates like string theory suggest the fundamental entities are not point-like particles but incredibly tiny, vibrating strings, with different vibrations corresponding to different particles. Others propose loop quantum gravity, where spacetime itself is woven from a fabric of discrete, finite loops. These are monumental ideas, but they remain untested by experiment, existing in the realm of beautiful mathematics. For now, we live with two separate maps of reality, each brilliantly accurate in its own domain. Yet together they paint a picture of a universe far stranger, far more interconnected, and far more mysterious than we ever dreamed. The chasm between quantum mechanics and general relativity may not be a flaw in our understanding, but a clue pointing to a reality far larger than our own. This leads to one of the most mind-expanding ideas in all of science, the multiverse hypothesis, the possibility that our entire cosmos is just one page in an infinite library of universes. This is not science fiction, but a speculative yet serious consequence of our best physical theories. The first compelling concept comes from cosmic inflation. Recall that brief, hyper-fast expansion of spacetime just after the Big Bang. Many cosmologists believe this inflation is not a one-time event but an eternal process. Picture a vast, bubbling cosmic foam. In this foam, new universes are constantly budding off from the inflating spacetime of a parent universe, like bubbles forming in a pot of boiling water. Each bubble universe inflates on its own, cooling and developing its own distinct laws of physics, its own fundamental constants, even its own number of dimensions. In this eternal inflation scenario, our universe is just one bubble in a frothing, unending cosmic sea, forever disconnected from its countless neighbors by ever-expanding walls of inflating space. A second, profoundly different idea emerges from the quantum weirdness we just explored. The many worlds interpretation of quantum mechanics takes the concept of superposition to its ultimate, dizzying conclusion. Remember that particle in a blend of states until observed. Many worlds suggests that every quantum possibility actually happens. At every quantum decision point, the universe splits. In one branch, you see the particle spin up. In another, perfectly real branch, you see it spin down. This happens for every quantum event, everywhere, all the time. In this view, there is a universe where you took a different job. A universe where the dinosaurs never went extinct. A universe where every possible outcome of every quantum roll of the dice is realized. Reality is not a single timeline, but a constantly branching tree of parallel worlds, all equally real, but forever inaccessible to one another. Then there is the vision from string theory, the candidate for a theory of everything. String theory requires extra spatial dimensions, curled up so small we cannot perceive them. The way these dimensions are folded could determine the laws of physics in a universe, like how the folds of an origami sculpture determine its final shape. The mathematics suggest there may be a staggering number of possible configurations, perhaps 10 to the 500 or more. Each configuration represents a different possible universe with its own unique physical laws. This is the string theory landscape, a cosmic catalog of possible realities, and our universe is simply one entry that happens to allow for stars, planets, and life. But are these scientific theories or untestable philosophy? The line is razor thin. True science requires predictions that can be verified or falsified. Some physicists suggest we might find evidence of a multiverse in subtle imprints on the cosmic microwave background, perhaps a bruise from a collision with another bubble universe in the distant past. Others argue that if the multiverse is real and contains every possible set of laws, then our existence itself becomes a form of evidence. We can only find ourselves in a universe whose constants, like the strength of gravity or the mass of the electron, are finely tuned to allow for our existence. This is the anthropic principle in a multiverse context. In an infinite array of universes, most would be sterile, empty, or stillborn. We are not here because our universe is special. We are here because it is one of the rare habitable ones. The implications are staggering. If true, the multiverse redefines reality on a scale that makes our observable cosmos seem like a single grain of sand on an endless beach. It suggests that every possible history, every possible version of you, and every imaginable physical law might exist somewhere in the greater whole. It challenges our deepest notions of uniqueness and meaning, placing our entire epic story from the Big Bang to the rise of civilization as just one narrative among an infinite number of untold tales. Given this infinite cosmic landscape, our own universe still has its own story to finish. The ultimate fate of everything we see is written in the balance between two titans, the relentless outward push of dark energy and the inward pull of gravity from all matter, both seen and unseen. Cosmologists call this the critical density, and our measurements point to a single, chilling conclusion. The expansion is not just continuing, it is accelerating, and that acceleration appears to be permanent. This leads us toward the most likely end, a scenario known as the Big Freeze or heat death. Picture the universe as an engine slowly running out of usable fuel. As space expands forever, galaxies will recede over the horizon of visibility, their light stretched beyond detection. Individual galaxies will grow dark as stars exhaust their nuclear fuel. Some will end as white dwarfs, cooling into black, crystalline spheres over trillions of years. Others will explode or collapse into black holes. Even these black holes are not eternal. Through the slow leak of Hawking radiation, they too will evaporate, a process that for the largest could take a googol of years, that is a 1 followed by 100 zeros. In the end, all that remains is a near-perfect vacuum, a sea of diluted photons and subatomic particles so far apart they will never interact again. The temperature of the entire cosmos approaches absolute zero. No more heat flows, no more work can be done. It is the ultimate state of maximum entropy, a static, silent, and eternal darkness where time itself may lose all meaning. This is the heat death, not a dramatic explosion, but a slow, irreversible fade to black. But our understanding of dark energy is still young, and other, more violent endings remain possible. What if dark energy is not constant, but grows stronger over time? This leads to the Big Rip. In this terrifying scenario, the repulsive force of dark energy would eventually overcome every force that holds things together. First, galaxy clusters would be torn apart, then individual galaxies. As the force intensifies, stars would be ripped from their orbits. In the final moments, planets would be shredded from their stars. Ultimately, the very fabric of space-time would stretch so violently that atoms, atomic nuclei, and even the fundamental particles themselves would be torn asunder. The universe would end not with a whimper, but with a catastrophic, instantaneous rupture of reality itself. There is also the poetic, symmetrical alternative, the Big Crunch. This was the favored model before the discovery of dark energy. If the density of matter had been high enough, gravity would have eventually halted the expansion and reversed it. Galaxies would begin rushing back together, space itself contracting. The cosmic microwave background would blue shift, heating the universe. Galaxies would merge in a reverse of the Big Bang, and the sky would glow hotter and hotter. Eventually, all matter and energy would be compressed back into an ultra-hot, ultra-dense state, perhaps another singularity, a cosmic reset button that could potentially trigger a new Big Bang and a new universe in an endless cycle. Current data, however, strongly disfavors this cyclical ending. The measured acceleration suggests the universe will expand forever. The timeline for any of these endings is beyond human comprehension. The last stars will not flicker out for another 100 trillion years. The evaporation of the largest black holes will take magnitudes longer. The heat death lies so far in the future that all of human history, all of stellar evolution, is less than the blink of an eye in comparison. Our universe is young, vibrant, and full of light, but its story, in the end, appears to be one of quiet dissolution into an endless, frozen night. Against the backdrop of an eternal, silent end, our universe's present is defined by spectacular, fleeting violence. The cosmic calm is punctuated by titanic detonations that, for a few seconds or weeks, outshine entire galaxies. The most familiar of these are supernova, the explosive deaths of stars, but they are not all the same. There are two primary pathways to this stellar doom. The first, known as a Type II supernova, is the collapse of a single, massive star at least 8 times heavier than our Sun. When its core fuses its way to iron and can generate no more energy, gravity wins catastrophically. The core collapses in less than a second, then rebounds in a shockwave that blasts the star's outer layers into space at nearly 1/10 the speed of light. That expanding shell of gas glowing for months is what we see from Earth, but there is another, even more crucial type. A Type 1, a supernova, involves a stellar corpse, a white dwarf in a binary system. If this dense remnant siphons enough material from its companion star, it can be pushed over a critical mass limit. The entire white dwarf then undergoes runaway nuclear fusion in a matter of seconds, detonating like a thermonuclear bomb of cosmic proportions. It is completely obliterated, leaving nothing behind. This specific kind of explosion is a cosmic benchmark. Because the white dwarf always explodes at the same critical mass, these supernovae always reach roughly the same peak brightness. This makes them standard candles, celestial lighthouses of known wattage that allow astronomers to measure vast distances across the universe. It was the careful observation of these very explosions that revealed the shocking acceleration of the cosmos, leading to the discovery of dark energy. Beyond their role as cosmic yardsticks, these explosions are the universe's primary forges. In the heart of a massive star and in the fury of its supernova, nuclear fusion creates elements up to iron. But the extreme conditions in the supernova blast itself, with its immense flux of neutrons, are where all heavier elements are born. Through a process called rapid neutron capture, atoms are bombarded, building gold, silver, platinum, uranium, and every other element on the periodic table beyond iron. This newly forged stardust is then hurled across interstellar space, eventually mixing into clouds of gas that will form new stars and planets. Every piece of gold jewelry and every uranium atom in the Earth's crust was created in one of these brief, apocalyptic flashes. Yet even a supernova is not the final word in cosmic violence. There exists a phenomenon so powerful it makes a supernova look like a firecracker. Gamma-ray bursts are the single most energetic explosions in the universe since the Big Bang itself. For anywhere from a few milliseconds to several minutes, they focus more energy than our Sun will emit in its entire 10 billion-year lifetime into two narrow, opposing beams of the highest frequency light. We see them as sudden, blinding flashes of gamma rays from random points in the sky, often billions of light-years away. For decades, their origin was a top mystery. Today, we believe most of these bursts come from two catastrophic events. The long-duration bursts, lasting more than 2 seconds, are thought to be hypernova, the collapse of a rapidly spinning, ultra-massive star into a black hole, directing its dying energy into jets that pierce through the star's poles. The short-duration bursts, lasting less than 2 seconds, are likely the result of something even more exotic, the merger of two neutron stars or a neutron star and a black hole. When these incredibly dense objects spiral together and collide, they create a black hole almost instantly, and the violent disruption sprays out a blitz of gamma rays and, as we have now detected, gravitational waves. These mergers are also thought to be cosmic gold mines, factories for heavy elements like gold and platinum, which are flung out in the neutron-rich debris. The sheer power of these events poses a hypothetical yet serious question for life in the universe. If a gamma-ray burst were to occur within our own galaxy and its deadly beam were pointed directly at Earth, the consequences would be catastrophic. The initial blast of radiation would strip away our planet's protective ozone layer for years, allowing intense ultraviolet radiation from the Sun to reach the surface. This could trigger a mass extinction, wiping out much of complex life. Some scientists speculate a gamma-ray burst from a few thousand light-years away may have contributed to the Ordovician extinction 450 million years ago. Fortunately, the odds of a direct hit from a nearby burst are astronomically low. We monitor the skies constantly with a fleet of satellites like NASA's Swift and Fermi observatories, which can pinpoint a burst within seconds and alert telescopes worldwide to swing toward its fading afterglow. These fleeting flashes are not just destructive curiosities, they are lighthouses from the far edges of time and space, illuminating the most extreme physics and reminding us that the cosmos, for all its serene beauty, is still a place of raw, untamed power. The most violent events in the cosmos do not just create light, they create sound. For a century, Einstein's theory predicted that cataclysms like colliding black holes would send literal ripples through the fabric of spacetime itself, gravitational waves. These are not waves of matter or light, but distortions in the geometry of the universe, stretching and squeezing space itself as they pass. Imagine the universe as a still pond. If you drop two heavy stones into the water, the ripples from each impact will spread outward, intersecting and warping the surface. A merging black hole binary is like those stones, only their mass warps the pond of spacetime itself. When two such incredibly dense objects like black holes or neutron stars spiral inward at nearly the speed of light, their violent acceleration sends powerful gravitational waves radiating outward at the speed of light, carrying the fingerprint of the collision across billions of light years. The catch is that these ripples are almost unimaginably tiny by the time they reach us. A passing gravitational wave from a distant merger might change the distance between you and a friend by less than the width of a single atomic nucleus. Detecting such a minuscule signal seemed impossible for decades. The breakthrough came with an instrument of breathtaking precision, LIGO, the Laser Interferometer Gravitational Wave Observatory. It does not look like a traditional telescope. Each LIGO site consists of two 4-kilometer-long vacuum tubes arranged in a giant L shape. A laser beam is split and sent down each arm, bouncing off perfectly suspended mirrors at the ends before recombining. In perfectly still spacetime, the light waves return and cancel each other out. But when a gravitational wave passes, it literally changes the length of one arm relative to the other by a minuscule amount. One arm gets stretched, the other squeezed. This changes the travel time of the laser light, so the recombined waves no longer cancel perfectly. A tiny flicker of light appears in the detector, a signature of spacetime itself ringing like a bell. To rule out local vibrations from trucks or earthquakes, two identical detectors operate in the United States, in Louisiana and Washington state, separated by 3,000 kilometers. A real gravitational wave will hit both with a characteristic delay. They are joined by Virgo, a similar detector in Italy, forming a global network that can triangulate the source of a wave in the sky. On September 14, 2015, after decades of development, this network heard its first clear note. The signal, named GW150914, lasted just 0.2 of a second. The waveform precisely matched the prediction for two black holes, one about 36 times the mass of the Sun, the other 29, spiraling together and merging over 1 billion light-years away. In that fraction of a second, an amount of energy equivalent to 3 times the mass of our Sun was converted into pure gravitational wave energy, shaking the cosmos. It was a direct confirmation of Einstein's prediction and the dawn of gravitational wave astronomy. Since then, the detectors have heard dozens of these cosmic chirps, each a unique story. We have listened to pairs of neutron stars colliding, events that also flash with light and are thought to forge heavy elements like gold. We have heard the uneven, lopsided merger of a black hole with a much smaller neutron star. This new sense allows us to perceive the dark universe. Traditional telescopes see the light from stars and gas, but gravitational wave observatories hear the gravity of invisible, massive objects in motion. They listen to the silent dance of black holes in the void, a symphony of warped spacetime playing just beneath the range of visible light. We are no longer just stargazers, we have become eavesdroppers on the fundamental vibrations of reality. That new sense of hearing the cosmos is complemented by a new eye, one that sees the universe in a color invisible to us. The James Webb Space Telescope is not merely an upgrade, it is a paradigm shift in how we observe the cosmos. While the Hubble Space Telescope showed us the universe in visible and ultraviolet light, Webb is an infrared telescope. Infrared light has longer wavelengths than visible light, and this simple fact gives it two superpowers. First, infrared light can pierce through the vast clouds of cosmic dust that obscure the nurseries where stars and planets are born. Hubble saw these nebulae as beautiful, opaque curtains. Webb sees right through them, revealing the infant stars forming within. Second, and most profound, is cosmological redshift. Because the universe is expanding, the light from the most distant, earliest galaxies has been stretched during its long journey to us. That original ultraviolet and visible light has been shifted all the way into the infrared part of the spectrum. To see the first galaxies, you must have an eye that sees infrared light. Webb is that eye, a time machine peering over 13 billion years into the past. Its early observations have already rewritten textbooks. In our own galactic neighborhood, Webb has turned its gaze to stellar nurseries like the pillars of creation in the Eagle Nebula. Where Hubble's iconic image showed majestic, shadowy columns silhouetted against glowing gas, Webb's infrared view is a revelation. The dust becomes semi-transparent, and thousands of previously hidden newborn stars sparkle like embedded jewels, their nascent jets carving cavities in the gas. We are witnessing the very process of stellar birth with unprecedented clarity. Beyond our galaxy, Webb has performed a feat once thought the realm of science fiction, analyzing the atmospheres of exoplanets hundreds of light years away. When a planet transits in front of its star, a tiny fraction of the star's light filters through the planet's atmosphere. Webb's exquisite instruments can split that light into a spectrum, a chemical barcode. In the atmosphere of the gas giant WASP-39b, Webb didn't just find water vapor, it made the first definitive detection of carbon dioxide in an exoplanet atmosphere. On the rocky world TRAPPIST-1b, it found no detectable atmosphere, a crucial data point in assessing the habitability of that fascinating system. This is no longer just about finding planets, it is about reading their stories, sniffing their air for the chemical signatures that might one day hint at life. But Webb's ultimate mission is to look back to find the cosmic dawn. Its first deep field image targeted a patch of sky no larger than a grain of sand held at arm's length. In that infinitesimal point, it revealed thousands of galaxies, a cosmic crowd stretching to the edge of time. Among them were fuzzy red smudges, galaxies so distant their light has traveled for over 13.4 billion years. We are seeing them as they were just 400 million years after the Big Bang, in an era when the universe was a mere 3% of its current age. These are not the majestic, well-ordered spirals we know today. They are small, chaotic, and bursting with star formation, the universe's first building blocks under construction. Webb has even spotted candidate galaxies that may be from an earlier time still, pushing our view closer than ever to that first generation of stars that ended the cosmic dark ages. Every image is a postcard from a younger, more violent universe, showing us the childhood of galactic structure. Positioned 1 million miles from Earth at the stable Lagrange point 2, with a sun shield the size of a tennis court protecting its golden mirror from the sun's heat, Webb operates in profound cold and darkness. It is our most ambitious window into cosmic history, a silent sentinel translating the infrared whispers of the infant cosmos into a story we can finally begin to understand. This breathtaking precision we observe is not a cosmic accident, but a profound puzzle. The fundamental forces and constants that govern our universe appear to be fine-tuned with almost unbelievable exactitude for the existence of complex life. If the strength of gravity were even slightly stronger, stars would burn through their fuel too quickly and collapse into black holes before life could arise. If it were slightly weaker, stars would never ignite at all, leaving the cosmos a dark, cold soup of hydrogen and helium. The same razor's edge applies to the nuclear forces. The strong force that binds atomic nuclei must be strong enough to overcome the repulsion between protons, but not so strong that all hydrogen would fuse into heavier elements in the Big Bang, leaving no fuel for stars. The cosmological constant, which governs the energy of empty space and drives the acceleration of the universe, is fine-tuned to an astonishing 1 part in 10 to the 120. That is a number so unimaginably precise it is like hitting a bullseye on a dartboard the size of the entire observable universe. This is the fine-tuning problem. It feels as though the dials of reality were set with deliberate, meticulous care to allow for galaxies, planets, and eventually, creatures who could look up and wonder why. One compelling response to this puzzle is the anthropic principle. In its simplest form, it states that we can only observe a universe that is compatible with our existence as observers. It is a selection effect. We are not here because the universe is special. The universe appears special because we are here to see it. If any of those fundamental constants were different, there would be no one to ask the question. In a multiverse containing a near-infinite variety of universes with different physical laws, we inevitably find ourselves in one of the rare habitable ones. This shifts the question from why our universe is fine-tuned to why we find ourselves in a fine-tuned universe. The answer becomes almost tautological. Yet this principle sparks intense debate. To some scientists, it is a powerful, even necessary, insight that explains the apparent coincidence without invoking a designer. It grounds our observations in the simple logic of our own existence. To others, it feels like a philosophical cop-out, an argument that halts scientific inquiry by saying the universe is the way it is because otherwise we would not be here to see it. They argue it does not explain why a multiverse should exist in the first place, or why the laws of physics allow for such a vast landscape of possibilities. The fine-tuning problem sits at the crossroads of physics, philosophy, and cosmology. It forces us to confront the deepest questions about our place in the cosmos. Are we the miraculous, intended outcome of a universe crafted with purpose? Or are we simply the lucky winners of a cosmic lottery with an almost infinite number of losing tickets? The search for an answer continues to drive our exploration, pushing us to look beyond our own universe for clues to the ultimate nature of reality. The fine-tuning of our universe suggests a story with a very specific beginning, a sequence of events so rapid and precise that it set the stage for everything to follow. To grasp this epic, we can compress the entire 13.8 billion-year history of the cosmos into a single calendar year, where the Big Bang strikes at the first instant of January 1st. In this cosmic calendar, every month represents over 1 billion years, every day about 40 million years. Our entire human civilization would not appear until the very last seconds of December 31st. Let us walk through this extraordinary timeline. The story begins not with a bang we can describe, but with the Planck epoch, the first incomprehensible fraction of a second after time zero. This is the realm of pure quantum gravity, where all 4 fundamental forces are unified and our current laws of physics offer no guide. It is over by 10 to the negative 43 seconds, a number so small it has no analogy in our world. Then comes inflation, a concept we have discussed, sometime before the universe is even a trillionth of a second old. A mysterious field of energy causes space itself to expand exponentially, smoothing out the cosmos and planting the quantum seeds for all future structure. When inflation ends, that energy is converted into a hot, dense soup of fundamental particles. We now enter the quark epoch. For the next several microseconds, the universe is a seething plasma of quarks, gluons, and other exotic particles, too hot and energetic to stick together. As expansion continues to cool things down, we cross into the hadron epoch. quarks finally combine to form protons and neutrons, the building blocks of atomic nuclei. For minutes, the universe is still hot enough for nuclear fusion to occur on a cosmic scale. This is Big Bang nucleosynthesis. Protons and neutrons fuse to form the nuclei of the lightest elements, hydrogen, helium, and trace amounts of lithium. In just those first few minutes, the basic chemical composition of the cosmos is set, with about 75% hydrogen and 25% helium by mass. The universe will cook no new elements for hundreds of millions of years. For the next 380,000 years, the universe remains an opaque fog. It is still so hot that electrons are ripped away from atomic nuclei, creating a plasma of charged particles that constantly scatter light, trapping it. The cosmos is a glowing, featureless sea. Then, a pivotal moment arrives: recombination. The expanding universe cools enough for electrons to finally combine with protons and helium nuclei, forming stable, neutral atoms. Suddenly, light can travel freely. That first flash of liberated light is what we see today as the cosmic microwave background, the afterglow of creation, released when the universe was a mere infant. On our cosmic calendar, this moment of first light occurs in late January. With the lights effectively turned off, the universe enters the cosmic dark ages. For over 100 million years, there are no stars, no galaxies, only vast, dark clouds of neutral hydrogen and helium gas, slowly cooling and beginning to clump under the gentle pull of dark matter's invisible scaffolding. The cosmos is silent and dark. Then, somewhere between 100 and 200 million years after the Big Bang, gravity wins in the densest knots of gas. The first stars ignite. These are not like our sun. They are population 3 stars, behemoths hundreds of times more massive, burning pure hydrogen and helium with a ferocious blue-white intensity. They live fast and die young in colossal supernova, polluting the pristine gas with the first heavy elements, the stardust for future generations. Their ultraviolet radiation begins to tear apart the surrounding neutral hydrogen, a process called reionization, slowly clearing the fog and making the universe transparent again to ultraviolet light. On our calendar, these first stars flicker to life sometime in March. Galaxies begin to assemble as these first stars gather into clusters, then merge into larger structures around the halos of dark matter. By the time the universe is about 1 billion years old, the epoch of reionization is largely complete and the cosmic web of galaxies is taking shape. Over the next several billion years, galaxies grow through mergers and collisions, their central black holes feeding and growing, shaping the majestic spirals and ellipticals we see today. Our own Milky Way galaxy is forming during this period, its history written in the orbits of its oldest stars. By September on our cosmic calendar, the universe looks broadly familiar, filled with evolving galaxies. Our own solar system is a very late arrival. The Sun and its planets do not begin to coalesce from a cloud of gas and dust enriched by generations of dead stars until early September. On our compressed timeline, Earth forms on September 2nd. Life emerges relatively quickly in cosmic terms, with the first simple cells appearing by late September. For eons, life remains microscopic. The dinosaurs rule the land in late December, but are gone by the afternoon of December 30th. All of recorded human history, from the first cities to the launch of the James Webb Space Telescope, occupies the last 14 seconds of December 31st. Every person you have ever known, every story ever told, every empire that rose and fell fits into that final, fleeting moment before midnight. This timeline is not just a list of dates. It is the singular narrative that connects the quantum flutter of inflation to the planets we walk on. It shows how the first 3 minutes set a chemical legacy, how the patience of the dark ages gave way to the first brilliant lights, and how every element in our bodies required the lives and deaths of countless stars across billions of years. We are not just living in the universe, we are a brief, conscious chapter in its autobiography, reading the story as we help write it. Yet for all the grand narratives and elegant theories, the cosmos still holds cards close to its chest. Beyond the edges of our maps lie phenomena so strange they defy our current understanding, reminding us that the universe is a place of endless surprise. One of the most electrifying modern mysteries is the fast radio burst. These are not the long, drawn-out signals of pulsars, but incredibly brief, intensely powerful blasts of radio waves that flash across the sky for mere milliseconds. In that fleeting instant, a single burst can release as much energy as our sun puts out over 3 days. They come from deep space, far beyond our galaxy, and most seem to be one-off events appearing once and never repeating from that same spot. A few, however, are repeaters, firing off signals from the same location at irregular intervals. What cosmic engine can produce such staggering power in such a short time and from such vast distances? Theories abound, from the catastrophic mergers of neutron stars to the violent outbursts from highly magnetized neutron stars called magnetars. Some have even speculated cautiously about artificial origins, though natural explanations are far more likely. The simple truth is we do not know. These flashes are like cosmic fingerprints at a crime scene, but we are still trying to figure out whose hand they belong to. Another profound puzzle is etched into the universe's oldest light. When scientists analyzed the detailed map of the cosmic microwave background from the Planck satellite, they found something unsettling. On the largest scales, the temperature fluctuations in this afterglow are not perfectly random as our standard models predict. Instead, they appear to align along a particular axis in space, a preferred direction that has been nicknamed the axis of evil. This alignment, if real, suggests a fundamental asymmetry in the cosmos, a crack in the principle that the universe should look the same in all directions. It could be a statistical fluke, a trick of the data, or it could point to something far deeper, a pre-inflationary structure imprinted on reality, or even evidence that our universe collided with another in the multiverse. It is an anomaly that cosmologists argue over, a ghost in the data that whispers our standard model might be incomplete. Closer to home, in our own solar system's backyard, we find a different kind of cliffhanger. Far beyond Neptune lies the Kuiper Belt, a vast donut-shaped region of icy leftovers from the solar system's formation. Models predict that the population of these icy objects should steadily increase as we look outward, then gradually taper off. But observations show something startling. At about 50 astronomical units from the Sun, roughly 50 times the Earth-Sun distance, the number of Kuiper Belt objects drops off a cliff. It is as if someone built a wall out there. One compelling, though unproven, hypothesis is the gravitational influence of an unseen planet. This hypothetical world, often called Planet 9, would be several times the mass of Earth on a distant, elongated orbit, its gravity shepherding the orbits of distant objects and perhaps sweeping the inner edge of the Kuiper Belt clean. The search for this potential new planet continues, a reminder that our own celestial neighborhood may still hide major secrets. And then there is the signal that started it all, the one that still haunts the search for extraterrestrial intelligence. On August 15, 1977, the Big Ear Radio Telescope at Ohio State University recorded a 72-second burst of radio waves that was so powerful and so perfectly matched the expected signature of an artificial signal that astronomer Jerry Amon circled it on the printout and wrote a single, famous word in the margin: "Wow." The signal came from the direction of the constellation Sagittarius, never repeated, and has never been satisfactorily explained by any natural phenomenon. It was not a repeating pattern like a pulsar, and it occupied a narrow band of the radio spectrum reserved for listening to the universe, a band where human-made interference is supposedly forbidden. Was it a fleeting broadcast from another civilization, a cosmic hello that came and went before we could answer? Or was it a bizarre, one-off natural event we still do not understand? Decades later, the WOW signal remains the most tantalizing, unexplained blip in the history of SETI, a solitary question mark hanging in the static. These mysteries are not failures of science, but its very lifeblood. They are the edges of the map where the dragons are drawn, the unanswered questions that push our telescopes to see farther, our theories to think deeper, and our imaginations to stretch wider. They prove that our ultimate guide to the universe must always include a chapter titled "We Do Not Know." That profound connection is written into our very atoms. The calcium in your bones, the iron in your blood, the oxygen you breathe, none of it was present at the beginning. Every element heavier than hydrogen and helium was forged in the nuclear furnaces of stars and scattered across the galaxy by their explosive deaths. You are, in the most literal sense, the universe becoming conscious of itself. You are a collection of ancient stardust that has assembled itself into a form that can look back at the night sky and wonder about its own origins. This is not poetry, it is physics. The carbon that forms the backbone of your DNA was created in a star that lived and died before our sun was born. The gold in a wedding ring was likely forged in the violent collision of two neutron stars. We are not separate from the cosmos, we are its most intricate and self-aware product. Our drive to understand this story is as old as humanity itself. For millennia, we looked up and wove myths. The stars were gods, ancestors, or animals painted on the celestial dome. The cosmos was a realm of meaning, intimately connected to our lives and fates. Then, beginning with pioneers like Copernicus and Galileo, a profound shift occurred. We realized Earth was not the center of all things, but a planet orbiting an ordinary star. This was the first great humbling, a cosmic demotion that removed us from a privileged position. Yet it was also the first great liberation, freeing our curiosity to ask real questions about a universe governed by physical laws. Each subsequent discovery widened the scale and deepened the mystery. We learned our sun is one of hundreds of billions in the Milky Way, and our galaxy is one of trillions in the observable universe. We learned we are living in the aftermath of a cosmic beginning and are headed toward a cold, distant end. This understanding can produce a profound sense of cosmic loneliness, the feeling that we are insignificant specks on a pale blue dot, adrift in an unimaginable void that does not know or care we exist. This perspective, often called the cosmological principle, suggests there is nothing special about our location or moment in time, and yet that very same understanding reveals our extraordinary significance. In all our searching across all our telescopes and probes, we have found no other instance of consciousness, no other civilization asking these questions. As far as we currently know, we are the universe's way of understanding its own story. We are the means by which the cosmos can contemplate its birth, marvel at its galaxies, and ponder its fate. That places an immense responsibility on our collective shoulders. The knowledge that we are star stuff does not diminish us, it ennobles our brief moment of awareness. It ties our personal stories to the grandest narrative of all, connecting the spark of a thought in your mind to the first spark of light after the Big Bang. It means that when we protect the fragile biosphere of our world, we are safeguarding a rare and precious chapter in cosmic history. When we reach out with science and art to comprehend the universe, we are fulfilling a role that matter has waited 13.8 billion years to achieve. We are the universe, temporarily structured into beings who can feel awe, who can love, and who can choose to keep looking up. This profound connection is not reserved for scientists with giant telescopes. You can step outside tonight and begin your own direct conversation with the cosmos. Practical astronomy is the great equalizer, transforming the overwhelming scale of the universe into a personal experience of wonder. You need no special equipment to start, just your own eyes and a clear, dark sky. Begin by simply learning the major constellations. These ancient patterns are your map to the heavens. On a summer evening, look for the three bright stars of the summer triangle. In winter, the mighty Orion the Hunter dominates the southern sky, his belt pointing to Sirius, the brightest star in our night sky. This act of recognition is the first step in building your own mental map of the galaxy. To enhance this journey, your smartphone is a powerful tool. Free apps like Skyview or Stellarium use your phone's GPS and gyroscope. Simply point your device at the sky, and the app overlays the names of stars, constellations, and planets right on your screen. It is like having a planetarium in your pocket, instantly demystifying the celestial sphere and showing you when the International Space Station will glide silently overhead. If you wish to see more, start not with a telescope but with a simple pair of binoculars. A decent pair of 7 by 50 or 10 by 50 binoculars will reveal a universe invisible to the naked eye. Turn them toward the Milky Way on a dark night, and you will see it resolve from a faint cloud into a countless swarm of individual stars. You can see the 4 largest moons of Jupiter dancing around the giant planet from night to night. You can find the Andromeda Galaxy, a faint smudge of light that is the most distant object most humans will ever see with their own eyes, a galaxy of 1 trillion stars over 2.5 million light-years away. Binoculars are portable, intuitive, and offer a breathtaking wide-field view that even advanced telescopes sometimes miss. When you are ready for a telescope, do not rush for high magnification. Aperture, the diameter of the main lens or mirror, is king. It determines how much light you gather. A good beginner scope is a 6 or 8-inch Dobsonian reflector. It is essentially a large light bucket on a simple, easy-to-point mount. With such an instrument, the rings of Saturn become a real, tangible thing you can see with your own eyes. You can trace the ice caps on Mars during its close approaches and study the intricate craters and mountains of our moon in stunning detail. The goal is not to see a Hubble-like image, but to have that authentic, personal connection with photons that have traveled across the solar system to reach your retina. Your exploration can go far beyond observing. You can become a citizen scientist and contribute directly to real cosmological research. Online platforms like Zooniverse host projects where anyone can help classify galaxies from telescope surveys, searching for strange shapes that indicate mergers or rare structures. You can scan data from NASA, a test satellite, helping to identify the telltale dips in starlight that signal a potential new exoplanet. There are projects to track lunar craters, identify solar storms, and even listen to radio telescope data for patterns. By participating, you are not just learning, you are adding to humanity's collective understanding of the universe. The night sky is a shared inheritance, a story that belongs to everyone. By learning its patterns, training your eyes on its depths, and perhaps even contributing to its study, you move from being a passive spectator to an active explorer. You reclaim that ancient human bond with the stars, now informed by the breathtaking narrative of cosmic evolution. The universe's story is not locked away in journals. It is written across the sky, waiting for you to look up and read your own line in its epic. Our cosmic curiosity is not a spectator sport, it is a call to action. The blueprints for humanity's next great leaps into the cosmos are already being drawn, transforming science fiction into engineering reality. The first and most immediate destination is a world we have not visited in over 50 years, our moon. NASA Artemis program is not a simple repeat of Apollo. Its goal is to establish a sustainable, long-term human presence on the lunar surface. The plan is a stepwise marvel of modern engineering. An uncrewed Orion capsule has already circled the moon and returned. Next, Artemis 2 will carry a crew on a lunar flyby. Then, Artemis 3 will land the first woman and the first person of color on the lunar South Pole, a region of permanent shadows that may hold vast reserves of water ice. This water is the key to everything. It can be split into hydrogen and oxygen for rocket fuel and breathable air, turning the moon into a cosmic gas station and proving ground for the technologies we will need to survive on Mars. The vision extends to a lunar gateway, a small space station in orbit around the moon that will serve as a staging post, science lab, and communications hub. This is not about planting flags, it is about learning to live and work off-world, using the moon as our backyard workshop for interplanetary travel. Mars is the horizon beyond the moon, while robotic rovers like Perseverance currently scour the surface for signs of ancient life and cache samples for a future return mission. The human mission architecture is taking shape. The challenge is immense. A round trip would take roughly 2 years, exposing astronauts to deep space radiation, prolonged microgravity, and profound psychological isolation. The spacecraft will need to be a self-contained biosphere, recycling every drop of water and molecule of oxygen. Landing on Mars is another monumental hurdle, as its thin atmosphere is too thick for simple retro-rockets but too thin for parachutes alone, requiring a complex, untested combination of technologies. Companies like SpaceX are developing fully reusable, massive starships designed to carry 100 people at a time, aiming to make a Martian city of 1 million people a reality within the next few decades. Whether that timeline holds or not, the direction is clear. Humanity is methodically building the toolkit to become a multiplanetary species, a necessary step to ensure the long-term survival of our civilization. Our robotic eyes will also grow sharper, peering deeper into cosmic history and the atmospheres of alien worlds. The successor to the James Webb Space Telescope is already taking shape. The Nancy Grace Roman Space Telescope, scheduled for launch in 2027, will have a field of view 100 times wider than Hubble's. Imagine taking a deep, wide-angle portrait of the universe. Roman will perform vast sky surveys, mapping the distribution of galaxies and dark matter with unprecedented precision and discovering thousands of new exoplanets. Its primary mission includes studying the mysterious nature of dark energy by measuring how cosmic structures have grown over time. It will act as a cosmic detective, piecing together the history of the universe's expansion and providing clues to its ultimate fate. Alongside Roman, giant ground-based telescopes like the extremely large telescope in Chile, with a mirror nearly the size of a baseball diamond, will directly image Earth like exoplanets, analyzing their atmospheres for biosignatures, the chemical signs of life. Further out on the timeline, the concepts become truly visionary. Breakthrough Starshot is a serious research initiative exploring the feasibility of interstellar travel within a single generation. The idea is to build a fleet of tiny, gram-scale spacecraft equipped with cameras and sensors, each attached to a light sail, a thin, reflective sheet. From Earth, a massive array of ground-based lasers would focus a powerful beam on the sails, accelerating this nanocraft fleet to 20% the speed of light. At that velocity, they could reach the Alpha Centauri star system, our nearest stellar neighbors, in just over 20 years. These star chips would then fly past any planets there, snapping pictures and collecting data, beaming it all back to Earth. It is a staggering engineering challenge, but it represents a fundamental shift in thinking, from building massive, slow ships to sending swarms of intelligent, disposable probes on one-way missions of discovery. Even more audacious are ideas for re-engineering our solar system. A Dyson sphere is a hypothetical megastructure that a sufficiently advanced civilization might build to capture the entire energy output of its star. We are not talking about a solid shell, but a vast swarm of energy collecting satellites orbiting the sun. While building one is far beyond our current capabilities, searching for their infrared signatures around distant stars is a key part of the hunt for advanced extraterrestrial intelligence. Closer to home, the concept of a space elevator captures the imagination. The idea is a cable anchored to the Earth's equator and extending tens of thousands of kilometers into space with a counterweight at the far end. Electric climbers would ride this cable, transporting people and cargo to orbit for a fraction of the cost and energy of rocket launches. The material needed for the tether would need to be stronger than anything we currently possess, but advances in carbon nanotubes offer a glimmer of possibility. These are not tomorrow's projects, but they are the kinds of dreams that chart the course for centuries to come. This trajectory, from lunar outposts to interstellar probes, paints a picture of a species refusing to be bound by its cradle. Each mission, each telescope, each speculative blueprint is a statement of hope and a testament to our innate curiosity. We are driven by the same wonder that made our ancestors connect the stars into stories, but now armed with the tools to actually visit them. Our cosmic destiny is not a prewritten fate, but a choice we make with every launch, every discovery, and every young mind that looks up at the moon and decides to build the engine that will take them there. The universe has given us a story 13.8 billion years long, and we have just begun to write the next chapter with our own hands. The universe is a story often misunderstood, its plot twisted by popular myths that linger in our collective imagination. Let's clear the cosmic air, starting with one of the most poetic misnomers, the dark side of the moon. We often hear about this mysterious, unseen hemisphere, but the truth is far less ominous. The moon is tidally locked to Earth, meaning it rotates on its axis in exactly the same time it takes to orbit our planet. This is why we only ever see one face. But that face is not in permanent shadow. During a new moon, when the side we see is dark, the so-called dark side is bathed in full sunlight. It experiences day and night just like the near side, a 2-week-long cycle of each. The real mystery is the far side, which we did not see until the Soviet Luna 3 probe photographed it in 1959, revealing a heavily cratered landscape quite different from the familiar Maria, or seas, we see from Earth. It is not dark, it is simply distant. Another pervasive myth is that space is a perfect, absolute vacuum. While it is emptier than any vacuum we can create on Earth, it is not truly empty. In the vast voids between galaxies, you might find only 1 or 2 hydrogen atoms per cubic meter. Closer to home, in our own solar system, the solar wind streams out from the sun, a thin plasma of charged particles. There is also interstellar dust, tiny grains of carbon and silicon, and a faint bath of radiation left over from the Big Bang. This near-nothingness has profound effects. It is why spacecraft need heat shields, as those few atoms strike at orbital velocities, creating immense friction and heat during re-entry. Space is not an empty stage, it is a very thin, dynamic medium. We have already touched on the Big Bang, but the misconception is so fundamental it bears repeating. That name itself is the culprit. It conjures an image of a gigantic bomb exploding in a pre-existing empty room. But the Big Bang was not an explosion in space. It was the rapid expansion of space itself. There was no center point in a void that things flew away from. Every point in the universe was, and still is, rushing away from every other point. A better, though still imperfect, name might be the everywhere stretch. The evidence is all around us, in the uniform cosmic microwave background and the redshift of distant galaxies, telling the story of the stretching fabric of reality, not shrapnel from a celestial detonation. Finally, let's talk about the breathtaking images from telescopes like Hubble and Webb. Those swirling nebulae in vibrant purples and glowing golds are often not what you would see with your own eyes. Many of these objects are too faint for our color receptors, emitting light in wavelengths invisible to us. The images are real data, but scientists assign colors to represent different elements or to highlight structural details. For instance, an image might map hydrogen alpha emission to red, oxygen to blue, and sulfur to green. This is called representative or false color, and it is not deception, it is translation. It allows us to see the chemistry and physics of a cosmic scene, turning invisible light into a visual story we can comprehend. The beauty is real, even if the specific palette is chosen to inform. By untangling these myths, we move closer to seeing the universe as it truly is, a place more wondrous and logical than any fiction. This grand narrative is not a collection of separate stories, but a single, flowing river from the first moment to the last. Every part of the cosmos is connected, each chapter written by the one before it and setting the stage for the next. The Big Bang was not just a beginning, it was a precise set of initial conditions. The slight unevenness in that primordial fire, imprinted during inflation, became the gravitational seeds. Dark matter, acting as an invisible scaffold, pulled normal matter into those seeds, allowing the first clouds of hydrogen and helium to collapse. Without that specific pattern from the beginning and the ghostly grip of dark matter, galaxies would never have formed. Within those first galaxies, gravity compressed gas into the first stars. Their nuclear furnaces did more than just light up the darkness. They performed the universe's first alchemy, fusing hydrogen and helium into heavier elements like carbon and oxygen. When those massive stars died in supernova, they scattered these new elements into space, enriching the cosmic gas with the raw materials for rocky planets and ultimately life. Our solar system is a direct product of that stellar recycling program, built from the ashes of generations of dead stars. The supermassive black holes at the centers of galaxies are not just passive monsters. They are active participants in galactic life. When they feed, they can unleash torrents of energy that heat surrounding gas, preventing it from cooling and forming new stars. This feedback mechanism helps regulate a galaxy's growth, determining its size and shape. A galaxy and its central black hole grow together, their fates entwined in a complex gravitational dance. And overarching it all is dark energy, the mysterious force woven into the fabric of space. Its repulsive push, dominant for the last several billion years, now dictates the universe's large-scale fate. It is accelerating the expansion, pulling galaxy clusters apart and determining the final destiny of everything dark matter helped to build. It is the closing paragraph of the cosmic story, written in invisible ink. To understand a planet, you must understand the star that forged its elements. To understand a star, you must understand the galaxy that birthed it. To understand a galaxy, you must understand the dark matter halo that holds it and the black hole that shapes its core. And to understand why galaxies are flying apart, you must confront the dark energy stretching the void between them. This is the interconnected cosmos. It is a system where the quantum rules of the infinitesimal set the stage for the gravitational ballet of the immense. The iron in your blood connects you to a supernova. The calcium in your bones links you to a red giant star. The very space that is expanding between galaxies is the same stage upon which your life plays out. We are not just observers of this system, we are a temporary, conscious expression of its most intricate processes. The universe is not a random assortment of wonders, it is a single, magnificent, and unified whole. From that first silent point of infinite potential to the silent, frozen and awaiting us trillions of years from now, we have traced the entire arc of existence. We witnessed space and time ignite in the Big Bang, watched gravity sculpt galaxies from quantum seeds, and saw stars live and die to forge the atoms of our world. We stared into the abyss of black holes, felt the ghostly pull of dark matter, and confronted the accelerating void of dark energy. We questioned the quantum rules that weave reality, and wondered if our universe is just one page in an infinite library. We searched the skies for other voices and found so far a profound and meaningful silence. This is the ultimate story, a narrative that connects the frantic dance of a quark to the majestic spin of a galaxy. It is a tale written in starlight and gravity, a chronicle where we are both the audience and a fleeting, conscious sentence in the text. The scale is beyond comprehension, a canvas 13.8 billion light-years wide and still expanding, yet every part of it, from the vast cosmic web to the DNA in your cells, is linked by the same elegant underlying laws. The beauty of this understanding is not that it makes us feel small, but that it makes us feel connected. We are the universe looking back at itself, a way for the cosmos to know its own beauty and mystery. That drive to explore, to point our telescopes at the void and send our robots to other worlds, is the universe's own curiosity manifest through us. It is a privilege to be alive at a time when we can map this epic, to stand on this pale blue dot and comprehend our place in the grand scheme. The journey does not end here. Every new observation, every whispered signal from a distant galaxy adds another line to the guide, so keep looking up. Keep wondering and share your biggest cosmic questions in the comments below. Let's keep this conversation, this shared exploration of everything going. If this journey through the cosmos resonated with you, please like this video, subscribe for more deep dives into reality, and share it with someone who gazes at the stars. Thank you for exploring everything.